are a couple more questions about essentially what's happening with the subspace projection. So maybe here's a picture that might explain a little bit better what's going on. Suppose we have all those points here, and I want to approximate them, right? Here's my origin. And I could go and, maybe pick this point here, and then approximate all the other points by that linear subspace that I get, right? So what now happens is that, all these points will have these residuals. Right? So these are the residuals now. Now what I can simply do is I can take these as new points. The first one's gone. These are the residuals. And I can then ask again, within the space spanned by these points, what's the next best one to pick to approximate the rest? And that's perfectly fine, because now any point that I might pick, maybe this guy here, is given by a linear combination of itself and that guy, right? And after picking the first two, I can pick the third one accordingly, and so on and so on and so on. Bottom line being, you basically iterate this, rank 1 approximation procedure on itself, and, after you twist the linear algebra long enough, you'll get exactly the Cholesky factorization updates. So, something like numerical recipes would have that in excruciating detail. Good. So, I hope that helps a little bit. Now, another way how you could go about solving very large optimization.
Question?
Yeah.
So I get all the math, but it's hard for me to get the connection to how you're using the basis to solve the original problem.
Oh, okay. Well, the thing is, if I know, okay. So suppose, for instance, I know afterwards that phi of x is going to be given by some of the coefficients beta I of x, phi of xi. Then I can, simply, then I have a lower rank problem, right? Because now I can simply also use w is given by a sum over, some coefficients gamma I, phi of xi, I equals 1 to n, and I now have an n-dimensional problem in which I solved it. N-dimensional optimization problem. That's one way to solve it. The other way to solve it is to, map from phi of x directly into this n-dimensional space. And then we are back in the linear feature space mapping. So that would be given by x being mapped into this matrix k and n minus 1/2. And then here we have, the vector k of x and little x. Right.
So that's equivalent to doing a pre-processing on the whole data.
Exactly.
And then running the same.
You're spot on. So if you have, some grid job which can do this, you just pre-process everything and things are good. The only problem is that this is actually a very expensive operation potentially, right? So sure, this is a triangular matrix, so you can solve that in order n squared time, but still pre-processing is now order n squared in the number of dimensions that you're using. So if you have essentially arbitrary amounts of time for pre-processing, this is good. If your instances come in and they are new, and you need to do instant responses, you're still screwed. But among the low-rank methods, this is pretty much one of the best techniques that you can use. The good thing is that then afterwards at test time, things are good, right? Because at test time, I can actually use this expansion here, right? And so at test time, it therefore follows that f of x, let me switch the font color again, is sum over gamma I k of xi with x. So this is cheap. But at trading time, you suffer greatly. Okay. So does that answer your question a little bit? Well, the other way is, of course, you have an implicit kernel, which is given by, k tilde of x and x prime is k of x capital X, k in n inverse k of x prime capital X. But I mean, you'd be insane to use that directly in optimization procedure. That's way too costly. So, one thing you could do is you could just use function values, and I'll just show you briefly on on a single slide what the idea is. So in some cases, evaluating k times alpha is cheap. In some case, k inverse times y is cheap. And so you just reparameterize like what I showed you on the beginning of today's class. And you substitute in the variables and you solve the optimization problem. That can be a lot faster. So popular example is when you do web spam filtering. So the idea is basically that people might create entire fake websites with content and all, and to make it look like the real thing, they link against each other and do all sorts of funny stuff. And then you want to essentially detect whether something is web spam. It's actually a little bit more complicated than what I just described, because basically those fake websites will link to the real thing. But since it's web spam, real websites will not link to the fake ones. So you can actually use that for regularization to your advantage, right? So you basically can use the fact that the linked will not, so the linkee, so to say, will not necessarily have the same label as the linker, but the linker might actually have the same label as the linkee. So you can use a few things in this direction to get better estimates. But overall, this gives you a pretty good estimator for web spam. I mean, by now it's a reasonably well-solved problem, and what people nowadays do is they pay to have links to web pages with high page rank. So if you have a popular web page, then you can make money by linking to spam from your home page. So what you, for instance, want to do if you want to know the going rates is you go to freelancer.com. Yeah, and you search for page rank, and you'll find out the going rates. And it goes something like, I need 100 links from web pages that have a page rank of at least 3 or 4 or 5, and I'm willing to pay so and so many dollars to receive those links. And yeah, some people are willing to do that. So occasionally I get requests whether I might want to link to other stuff from my homepage, but thank you, no. So if any spammer hears this class, I hope they will stop spamming me. Now, another thing that you could do is you could actually, use, compression through hashing to do very efficient estimation. And to explain a little bit why this matters, let me quickly give you a bit of a motivation, namely multitask learning. So for those of you who have collaborative filtering projects and personalization, this is actually relevant. This is sort of the first step towards personalization. So let's say it's some email and it's actually received by users. And those users classify things as maybe spam or not, right? And yes, obviously it. Because spammers have email accounts too. They even have email accounts where you need to pay for, because they pay with stolen credit cards, right? the problem is that a lot of people basically don't label their emails. When was the last time you labeled an email as spam or ham? Who labeled one this month? Wow, you guys are good. At least 1/5 of you did this. Now, but this is a huge problem. So, you know, how should you solve it? Because, I mean, they don't tell you, I'm the spammer. So, here's how you can solve it. You basically give each his own classifier. So in that case, the spammer gets spam, and the one who doesn't like spam doesn't get spam. That's a big problem. How many emails, who labeled more than 10 emails as spam over the past 10 years? Who labeled more than 100 emails as spam over the past 10 years? Okay, so you're quite a standout, and as a matter of fact, we'll see afterwards a curve which has exactly that behavior. So you're one of those few highly desirable users for a mail service. So on behalf of Gmail and Yahoo Mail and IOL, I would like to thank you. So
I have 6 Gmail email accounts.
wow.
I have to do this. I integrate all of them into Gmail. I have to classify it. So.
Okay. So of course the problem is that you can't really classify everything perfectly for each user because you don't have very little data. So what we really get is a multitask learning problem. And this is actually the simplest version of the multitask learning problem because all the tasks are more or less the same. I mean, some tasks are really, identical. Some are maybe a little bit different because even spammers, I mean, they maybe like their own spam, but they don't like the other spam, right? So they don't want the other guy's spam to get through. They want only their spam to be, received properly. So quite often they will actually help you. So the idea is to have one, giant global classifier, and then some adjustment for everyone. And that type of, ranking or annotation problem you have quite often. If you think about web page ranking, right? I mean, we all have our own ideas of what is relevant or not. But by and large, we can agree on the things that are really boring, that you really wouldn't like to see. I mean, you might argue about, the top 5 positions, but overall, I think we're all quite similar. Unless we're the spammers, of course. So, how can we achieve this? So, one way is, we take this email, and we have, one global parameter vector W, and we have one parameter vector W for the user. Right. So that's what we get here. F of x and u is just, phi of x dot w plus phi of x dot wu. So each user gets its own parameter vector. Now I can rewrite that as phi of x tensor, 1 plus the entity vector for that user dot some, actually new parameter vector. So just show you pictures what happens. Right. So we basically map into some, giant space. Where now all the parameter vectors are stacked together into one giant monstrous parameter vector, right? So we have the global one, then user 1 gets his place, user 2 gets his place, and so on and so on. Right. This is huge. Like, this could be like 10 to the 13 dimensions, right? Crazy. Like 40 terabytes of space. And, well, correspondingly, the data is now the email. And then its text is actually replicated at the position of the user. So, show you in pictures what happens. We basically have x is being mapped into this long vector x, where it has its own copy again. Then there's a lot of zeros. Then there's x again for that particular user. And then there's a lot of zeros again. That's again. So this, maybe 10 to the 13 dimensional vector is essentially all 0 and except for, that one user and itself have a non-zero interest. And I could just solve that classification problem. Well, if I had 40 terabytes of RAM, which of course you don't have. So how do we fix it?
show how to compute the dimension. That's the dimension of the tensor space.
Yeah, exactly. So the idea is essentially, you might have a couple of million dimensions of, 10 to the 6, 10 to the 7 for the emails, just in terms of the words. And okay, so we have 10. Let's say we have 10 to the 7, and then if I have a million users, that's another 10 to the 6 right here. So if I have maybe 100 million users and a million dimensions, then that's already 10 to the 14. So this is a conservative estimate.
But the thing is, we only use rank 1 tensor in the tensor space. So basically, we don't care about the dimension of the ambient space. We care about the dimension of the primary.
Yeah. So however, well, so the thing is, the data, the email itself doesn't get him, storing that in this ridiculously high dimensional space isn't so expensive, because I just, need to get my point. As let's say I get an email with 100 words, then, at worst I need basically 200 pointers for that. So that's not so bad. But the W vector still needs to store everything. So storing all the parameters for all users is hopeless. You can't. So now the question is, can we do something to make this vector small enough? So some of you might have heard of locally sensitive hashing, for instance. And that sounds like the perfect candidate to do something about this, right? Because LSH will essentially take your ridiculously high dimensional data and it'll map it into a low dimensional space. Now LSH is sort of nice in the sense that it does that. And it actually maps into a really low dimensional space if you think about it, like thousands. But that's overkill because we actually have maybe 8, 16, 32 gigabytes of RAM available. So we don't need to map into a space that's counted by the thousands, but we can easily map into a space that, has a billion dimensions. So it's perfectly fine if we map from 10 to the 13 to 10 to the 9, or 10 to the 10. That's okay. We just can't keep it at 10 to the 13. As a matter of fact, the less compression I have to do, the better, because the more information I still will be able to retain. So let's see how we can actually do this without being too ham-fisted about computing. So this is where hashing comes in. So let's say we get that email, right? And let's say Barney receives that. And Barney might have an idea about whether this is spam or not. So what we do is, let's say the word mention is now mapped, I mean, we're not going to do this explicitly, but just, for a thought experiment, assume we take the word mention, and we have to look it up in our dictionary at which position in the vector it goes. Say it goes at position 1. And the combination of, task Barney and the word mention goes maybe somewhere here. And we do that for each word, and so we get some ridiculously sparse vector. And we have a dictionary that's, insanely large. I mean, it has like 10 to the 13 entries. So even the lookup data is already hideous. There we go. Take the sparse vector. Suppose we actually did this at some point, preprocessing. And we hash each of those coordinates to a hash function. And we map it into a sparse lower dimensional vector. So those of you who went to John Langford's VW talk would have probably seen something like this. I don't know whether he went into a lot of detail about hashing, but VW, for instance, also does this. Just be very careful about the options and user interface. It may fail in interesting ways without telling you so. But when it works, it's beautiful. So, here, so we do this, and we basically hash each of those coordinates, and we map in here. Now, occasionally you might get a collision, in which case we just add up the terms. Now, this actually looks like a really stupid idea, right? Because we first spend all this computation on the dictionary, map into this intermediate, very high dimensional vector, just in order to trash everything in the end again, and map into low dimensional space. So we don't actually need that dictionary. Let's get rid of it. So we just take the strings directly, like mention, or mention Barney. We hash it. and we map into this vector. The other twist that we do is we basically multiply it by some random of a hash s sigma, which basically here mentioned bar hash or sigma. So this is like this plus minus 1 value hash function. So if you recall the count hash of count sketch of Charika, Chen, and Farad Colton when we did the data streams, that's exactly the same data structure, except that we only use one hash. Yep.
What's the intuition behind the Rademacher hash for that?
I'll show you in a slide or two, but basically the idea is this way two vectors which are orthogonal will remain orthogonal in expectation. And I'll show you that in a slide or two. So, and then afterwards when you have to compute the function value, so f of x, now rather than computing, wi xi, this is the expansion that you now need to do. You do the lookup of w bar, which is the corresponding parameter vector of hash of I times sigma I xi. So you never really construct this vector, you just implicitly, go through all the non-zero coefficients as you go along. It makes your life a lot easier. Now, why would you not want to hash? Well, why would you want to hash? Well, the first thing is you don't need any dictionary anymore. So that means if I have a new word occurring that wasn't in my dictionary before, well, with that it's very easy because I can just, compute the hash of it and I know immediately where it goes. I might not have a very meaningful parameter stored for it at that location, but at least I know where it has to go. The second thing is I'm now able to use all the memory that I have for classification. So because otherwise, you might have sometimes had to use a lot of memory for your intermediate data structure, like your dictionary. But now you can actually use everything for the estimation directly. And furthermore, well, if you have a finite amount of memory, right, then, because, maybe you only get 8 gigabytes and that's all that the engineers gave you, then you can make your algorithm fit into this footprint. And that's actually a big deal. Even better, we don't need any memory for the projection matrix. Locally sensitive hashing may or may not require it. And we implicitly map into them space and preserve sparsity. So what I mean by sparsity preserving, since each non-zero coefficient is only really used once, we know that the number of non-zeros of the hashed vector is never higher than of the original vector. If I use LSH, locality sensitive hashing, this is not necessarily true. I may end up with a vector with considerably more non-zeros after hashing than would have had otherwise. So those of you who haven't heard of LSH, don't worry. But for those of you who do, well, yes, for certain theoretical guarantees, you would really like to be able to use a sparsified version of LSH, but computationally it's just infeasible, and there's no way I can actually go to my engineers and tell them, well, look, would you like to have an algorithm that takes 40 times as long, because maybe that's what we need for my guarantees to go through? That doesn't work any better. In practice, it doesn't work any better. Okay. So let's just look at why we need the sigma. If you think about it, that's the unhashed inner product, so sum over I, wxi. The hashed inner product, if I were to just take w and x, hash both, and take the inner product of that hashed space, it's just this, right? We sum over all the coordinates in the hashed space. Now, we need to sum over all the i's for which hash of I equals j. We take wi times sigma of I, so that's the Rademacher hash, like what's here. Now, if I take an expectation over all those, the hash functions, we can immediately see that, since this is a Rademacher hash. This is only going to be 1 if I equals I prime and 0 otherwise. Because if I is not equal to I prime, those binary signs are going to be uncorrelated. If I equals I prime, they're going to be the same. So this now preserves the inner product. Okay. And if I take an expectation over this, then that sum becomes, I get basically delta I prime, so the only term that survives is wi xi, and the derivative is fine. Okay. Does that make a little bit of sense? Any questions? Yeah.
Could you explain what the indices mean?
Okay. The indices are just coordinates in W or X. So if I have a 1,000-dimensional vector, I goes from 1 to 1,000. If I have a document, then I goes over all the words in the document, for instance, for a bag of words representation. And
So
J is the value of the hash. So, and because basically I need to sum over all the indices I that collide with each other into the bin J. Right? That's why I get this expression here. So to find out the Jth coordinate of W bar, which is the hash version, I need to find all the coordinates I that collide with each other and amount to J. And I have to take their value, multiply it by this Rademacher hash, and sum it up. Ditto here. However, in expectation, these things are 1 if and only if I equals I prime, because if these indices match up, and 0 otherwise. So the funny story is that initially when we did this hashing, we didn't have those signs. And after we added them, not only did the proofs become insanely much simpler, it also worked a bit better. But the biggest simplification was actually the proofs. They worked a bit better. But it wasn't quite like that. So what really happens is, if we have two vectors that are orthogonal in high dimensional space, then through the hashing they're approximately orthogonal in the lower dimensional space, so we can do very efficient multitask learning. And if we had two vectors that were orthogonal before, namely, let's say the parameter weight vector for user V and the feature vector for user U, then in the hashed space, well, the inner product is essentially going to vanish with high probability. If you want to get the variance of this entire hash expression, well, you have to sit down and either use Maple or just work it through. There isn't really much instructive stuff to be learned at that. I mean, you just have to work through all the coefficients and you get that basically order 1 away. Then there's a soda paper, which is probably about 12 or 15 pages of fairly sophisticated math, which shows that actually a variant of this retains the restricted isometry property. In other words, with high probability, also the tails are okay, rather than just the means and variances. Well, that's all very well, but does it actually work? So, here are some examples, right? So, the black line is basically, without hashing, the baseline, the unpersonalized distribution. This is the number of bits in the hash table, so basically 2 to the number of that gives you the number of dimensions into which we fit. So this is not very high, right? That's like 1,000,000 dimensions. And it's a small data set, so 20 million emails, 400,000 users. Very small example, but yeah, they didn't let us publish anything else for obvious reasons. And the spam miss rates are normalized to 1, because of course this is, secret how good our spam filters actually are. But the one thing you can see is, let's look at the blue line first. That's basically a hashed version of the unpersonalized spam filter. You can see that about 4 million dimensions, it works as well as the correct way. Now, in the personalized case, we couldn't really compute such a baseline because it would have been way too high dimension. It would have been basically 400,000 times a billion, right? So it would have been 400 billion dimensions, and we don't have good enough computers for that. So, however, for hashing, as you can see, you crank up the number of dimensions more and more, and things do get better. And here, okay, it's only slight improvements. Now, the big problem, however, is exactly this one here. So, this is our typical user base. And as we saw before in the very subjective poll, very few users are actually very diligent and label everything. I mean, yes, we love those users a lot, but unfortunately we don't have many of them. That's a log-scale number of users, number of labels that they apply. So let's see, does it actually even help the users that don't get even a single email? And you can simulate that simply by taking that one single labeled email out and treating the user as unlabeled and then checking for that email. And what you can see is everybody benefits. Right. So even those users who don't label anything get the reduction in spam. Those users who label a lot get the most reduction, which is great, but even the lazy ones benefit. Now why might that be the case? Well, one thing is that sometimes people who label a lot are not just really good users, they might have very peculiar email tastes. They might just have very strange email tastes and decide that they want to receive emails about how they can get their degree very efficiently or enhance body parts. Or they might actually be outright spammers. So at that point, they get their own personalized spam filter, and nobody else really suffers very much from it. And that's why personalization helps everybody, even those people who aren't really adding much more data. Okay. So, any questions at the moment? Okay, good. So, you can actually use hashing for a lot of other things. So let's say I want to, do string comparison, and spammers are a crafty bunch, and they will change words. And rather than Berkeley, you can insert the word Viagra, and you can immediately also see all sorts of variations. And you've probably seen them all in the email. So you want to really have, a feature map in your similarity measure that really catches all of these guys. And all of those are obviously different from the original word. So how can I get it? The idea is, you have some kernel between x and x prime. And so what I do is I just look at all modifications or substrings of x and all modifications substrings of x prime. Then I compute this. And as long as, those strings are close, things are good. So how can we catch them all? Well, one way of going about it is we just weigh maybe by some mismatch count, and we map the data into fragments. So for instance, if I have the word dog, I could map it into star og, into d star g, or into star. And then I hash those fragments, and weigh them accordingly. And the good thing is that this allows me to get something that's exponential in the alphabet size. It catches elements that are exponential in the alphabet size, but I only have a polynomial growth in the number of positions that I allow for mismatch. So back to Berkeley. Well, here's what we do. Right? So in all of those cases, the original word will match this. If I want to filter out Berkeley and decide, this is a more relevant word, well, I will catch it. And this gives you very efficient approximate string matching. Occasionally people still write papers on other techniques for fast string matching, but this is actually a lot more efficient. There are a couple of other details about memory access patterns, and I'm not going to go much in detail, so you can just look it up later on if you want. But suffice it to say, you can actually use cryptography to speed up memory access. Essentially, the idea is if you have to do many memory accesses, you can essentially use encryption to limit the range in which the keys go, and then just solve the problem again. Yeah. Good. So I think now's actually a good time to have a short break. Yeah, so let's meet again in 5 seconds.